Good afternoon, everybody, and welcome to the first Hartwig virtual training class of 2021. Today, we're going to cover Okuma Lathe multifunction programming. My name is Ricky Hochecker. I'm an applications engineer here at Hartwig, and I will be presenting today's information. We also have Joe Million in the background producing today's training class. If you have any questions, please feel free to type them in the chat, and throughout the presentation, we will pause to answer questions, and Joe will be able to read those off or post them live if the answer is good information for everybody to have. After this presentation's over, we will follow up with an email with all of the questions and answers from today's presentation, as well as a PDF of the presentation and a quick survey. We would really appreciate if you guys reply with the survey and let us know how we're doing. Let us know if there's anything you want to see we didn't cover or anything we could do better. Hartwig helps people in manufacturing control their destiny every day. And that's our goal with these classes, is to reach out to you as our customers and give you guys a resource during a challenging time when we can't have classes in the offices in person. So we hope that you get a lot of good information out of this. And even after this presentation's over, if you have any questions or you need some help further beyond the presentation, please feel free to reach out to any of us. We'll be more than happy to help you in any way we can. Before we talk about actually writing a program for a multifunction lathe, the first thing we need to understand are some of the G-codes that are used associated with these machines. So G136 will turn off the y-axis or coordinate conversion function. Now, what this does essentially is take y-axis to 0, or start reading code in the XZ plane again, instead of XY as coordinate conversion would do. G137 is coordinate conversion on. This is typically followed by a C command for the orientation of the part. And with coordinate conversion, you can take a live tool lathe without y-axis, program XY coordinate points, and the machine will translate that to C-axis motion for milling a square or a hex or some other complex shape. G138 turns on the y-axis command. It's important to note when programming with the y-axis that the X coordinate on the machine tool, once y-axis is turned on, becomes radius. You'll see your control go from XA to XIA on the display, and that tells you that you are now in radius. To turn the spindle on clockwise is M13, counterclockwise is M14, and off would be M12 in reference to your live tool spindle. To perform C-axis milling, M110 engages the C-axis joint. You must use M110 to engage the C-axis before turning on the live tool spindle, or the machine will alarm out. Just the same, you must turn off the live tool spindle before commanding M109 to release the C-axis joint, or the machine will alarm. If you're doing some heavy milling in one specific orientation or drilling on the outside of a part and you don't want the part to roll maybe a little bit if the C-axis is only being held by the servo motor, you can also clamp the C-axis with M147 and unclamp the C-axis with M146. Another function on only the newer P300 controls that's really nice to use on multifunction lathes is machining mode designation function. This is essentially a G-code macro that you command one code based on what type of machining you intend to do going forward in the program until you change modes again, and the machine will command the code necessary to put the machine in that state. So G270 turning mode would cancel coordinate conversion or y-axis, G137 or 138, using G136, and it will release the C-axis joint with M109. G271 is C-axis machining mode, so this will command M110 to engage the C-axis joint, and G136 to cancel y-axis mode. G272 is y-axis machining mode. This will command M110 to engage the C-axis joint and G138 to turn on the y-axis at the same time. It's really nice. Now you only have to remember one code, put it at the top of the block, and the machine is in the mode prepared for you to write your code below. If you have a sub-spindle machine or a right spindle machine, you must also designate SP equals in the program to determine which spindle to change modes. We can also use fixed cycles when programming a multifunction lathe. G180 is fixed cycle cancel. G181 would be a straight drilling cycle. G183 would be your deep hole drilling cycle, is what most people refer to it as, or a drilling cycle with pecking. G184 is tapping, but controlled by a parameter. So you may be familiar with floating collets. With G184, you can set a parameter to float, and you can float tap in a live tool lathe. You can also set that parameter to concurrent and synchronize tap with G184. Now, if I intend to synchronize tap, me personally, because I want to standardize the program across all machines it may run on, I prefer to use G178 and G179, which is always synchronized tapping. For all of the above cycles, you can also use a Q value for the number of holes equally spaced around the part. And the machine will take 360 divided by the number of holes. In this example, we're using 6. And the result would be 60 degrees in this case. So 6 holes will be drilled every 60 degrees, starting from my coordinate C0, drilling to Z of minus 2.5 inches on a 2-inch diameter bolt hole circle. This is the parameter I was talking about for G184 tapping or G298 for left-handed tapping. Float is your typical floating holder. The difference is you cannot re-tap a hole in the machine with a floating holder. There's no way to pick up that lead again. Versus rigid tapping, you can use peck tapping, which means you can chase back through the hole. For such as an application of deep hole tapping, you could tap in, retract, 3 or 4 pecks to get to depth instead of having to take one full depth, say 2, 3, or 4 inches deep if necessary. That can be a really nice feature of rigid tapping on these machines. Something else to be aware of on a live tool lathe is the ability to reverse the direction of your live tool spindle. Within all the fixed cycles I talked about a couple slides ago, the machine will actually turn on the spindle of the lathe, the live tool of the lathe, in the M13 direction for any drilling operations. Now, if you are using a standard velocity live tool, that's okay, because the tool is set up for the way the machine is programmed for M13 to be clockwise rotation, which will drill a hole. But if you're using aftermarket holders, for instance, Kennametal's holders, you have to use this parameter. You would check mark the station that you've mounted the holder on, and that will reverse the rotation of the servo motor that's driving that live tool because if you leave it at the standard direction, when you command M13, the tool will rotate counterclockwise, which will break your drill. So even if you tried to use M14 to run the spindle the proper direction, as soon as you go to use a fixed cycle, such as G181, to drill a hole, the machine will rotate the spindle back to M13, breaking your drill if you do not reverse the direction of rotation on this parameter here. Again, you just check mark the station of which the tool is mounted in, and then the machine's ready to run. So this is a sample program where I'm using some live tool to drill a hole on the face of the part. So I have a nice little heading. I like to put a heading with the programmer's initials, the part number, the date, just some relevant information. And we have a tools list. We're going to have a rough turning operation, a finish turning operation, and drill a 1/2 inch hole. So I'm going to skip through the turning portion. Should look fairly familiar. We have a G85 rough turning cycle, lap cycle, and we have a G87 finish turning lap cycle to do the profile of the part. Then when we get to NAT3, our 1/2 inch diameter carbide drill, the first line of code returns the machine to the X limit and Z limit. The next line is G271 SP equals 1. What this means is C-axis machining mode on spindle number 1, my left spindle. Then we call up tool 3 offset 3. With SB equals, we are setting the spindle speed of the live tool. SB in this case equals 3,400 RPM to my live tool. And M13 says spindle on clockwise. Then we have a rapid move to 1 inches 260 in diameter and 100 thousandths away from the end of the part, turning coolant on. Our G181 is going to be a drill with no peck at a diameter of X 1 inch 260 to a depth of -1 inch 150 at C0 with a return plane of 100 thousandths and a feed rate of 5 thousandths per rev. Now K would be a shift amount. So let's say we're drilling down inside of a counterbore that's a 1/2 inch deep. I don't want to have to cut air for the first 1/2 inch of my drill. So I could put K of 0.5 or a 1/2 inch, and my drill would wrap at a 1/2 inch, then drill to the depth of -1 inch 150. Since we're drilling from the face of the part to depth, K is 0. G180 cancels my fixed cycle, return to the limit and turn off the live tool spindle with M12. Then G270 is turning mode. So release my C-axis joint on spindle 1. Let's take a look at what this program looks like running. Here comes our live tool. C-axis is engaged. Live tool drilled the hole. And then C-axis was disengaged and the spindle was turned off. Do we have any questions so far, Joe?
None so far, Ricky.
Thank you. We'll keep moving on then. This is a little more complex multifunction lathe program. I've only put the live tool portion in, so you will see a rough turning operation in the simulation after we talk about the code. There will be a finish turn operation and there will be a grooving operation. But we're going to focus on the live tool portion of this program. At the top of my left column, you see CRC equals 1.5 divided by 2. This is my cutter radius comp value. I'm using a local variable for this. So I'm saying local variable CRC is set equal to 1.5 inch diameter cutter, but I want to compensate for the radius, so I'm dividing by 2. The machine control will read this command and recognize CRC from this point forward in the program as 1.5 divided by 2. Now in NAT4, we're going to mill a flat with 1.5 inch shoulder mill. So the first line of code will rapid to the X limit and Z limit. We'll activate turret station 4, offset number 4 is going to be our live tool. M110 will engage the C-axis joint to get ready for our milling operation. SB equals 6,000. This is the max RPM of your live tool if you have a Genos L machine or an LB 3000, 4000 live tool lathe. This will be the max RPM of your live tool. So in this program, SB equals 6,000. M13 to turn on my tool clockwise. Then we see a rapid move to X of 4 inches 200 thousandths. This would be 100 thousandths away from the diameter of my part. To Z of 100 thousandths plus CRC. So I want the left side of my tool to be 100 thousandths off my workpiece. G138 will turn on the Y-axis mode. And then we're rapiding Y-axis to a coordinate point of -2 inches minus the radius of my tool. Z steps back to 1 inch plus the radius of my tool. G1, G94, so now we're changing the machine to feed per minute mode down to a radius, because we're in Y-axis mode now, of 1 inch is 900 thousandths. So this is a 100 thousandths depth of cut pass, feeding down at 45 inches per minute. Then the Y-axis will feed up at 90 inches a minute. The Z-axis will go to the left. Y will feed back down, and we're going to zigzag this flat the entire time, compensating for the radius of our tool. Once we reach the shoulder, we have a rapid move to X of 2.1. Now, this is 2.1 in radius still, so this is back to our return plane of 4 inches 200 thousandths in diameter. Rapid back to the front of the part, feed down another 100 thousandths, and take a second pass, repeating the zigzag. In this program, we're taking 4 passes. Once the 4th pass has been completed, then we rapid to our clearance plane, 2 inches 100 thousandths in radius, 100 thousandths plus the radius of the tool off the end of our workpiece. G136 cancels Y-axis mode, which will cause the machine to bring Y back to 0 from wherever it is. And then M109 will release the C-axis joint, and M12 turns off the spindle. Then we have to drill 2 off-center holes. So rapid to the X limit and Z limit. Call up tool 5, offset number 5 this time to drill our holes. M110 will engage the C-axis. SB equals 3,500, storing our live tool RPM now at 3,500. M13 for clockwise again. This time we're in feed per rev mode, G95, rapid to our clearance plane, and to the Z location of the first hole, -1 inch. G138 turns on Y-axis mode, and the first hole is offset 700 thousandths from center line, Y -0.7. G181 is again a live tool drill cycle, so we're going to drill a hole 1 inch deep at this location at C0. Then we're going to go to Y of 700 thousandths above center line, Z -4 inches, and drill another hole 1 inch deep. G180 will cancel the fixed cycle. G136 will again have Y-axis come back to 0 and turn off Y mode. M109 will release the C-axis joint, and then M12 will turn off the live tool spindle. Let's take a look at how this part will run. So here's our rough, finish, and then grooving cycle that were not in the sample program. Now here comes our live tool. Y-axis mode's on. You'll notice on the left side of the control, XIA has come up and the diameter was cut in half. And our last pass, Y goes to 0. Here comes our drill off center. And that's our sample part. Does anybody have any questions about that, Joe?
I don't see any questions that have come in, but it does look like we've got some graphic card artifacting or something going on from your end.
Yeah, I don't know what happened to that last simulation. It didn't run like that before. Hopefully the presentation will be okay from this point forward.
Okay, I'll let you know. That looks good.
Yeah, something with that video. So one other thing to talk about, a Y-axis machine isn't just good for live tool Y-axis milling. It also has a function called Y-axis offset turning. This allows you, such as the picture here, to stack two turning tools, one on top of the other, in a block. In this case, this is a sub-spindle lathe. There are 4 turning tools, rough and finish for main, and rough and finish for sub, stacked in this one turret station. Using the Y-axis offset, YI, in the tool offset chart below, you can tell the machine from Y0 the position of the tip of each tool. Then when you activate the tool offset, the Y-axis will slide down to put the tool tip on center line to turn your workpiece. The only thing to note is down in the corner, you must cancel tool offset for Y to return to 0 before indexing to the next station. So when you cancel the tool offset, you then have to tell the machine to go to Y0 and to take X back to the X limit, because as Y goes back to 0, X will fall off of your positive limit and your turret will not be able to index. This can be great for high production, high amount of tools, feel like you're running out of tools in the station, applications such as that. Where this is limited is when you get into large diameter workpieces, you can have interference between the turning tools. So you really have to look at the application of whether it's cost effective to purchase a block like this and set up Y-axis offset turning, or if you're better off having separate tools in separate stations. Are there any questions before we go on to sub-spindle?
None yet.
None yet. All right. For those of you who do not have a sub-spindle lathe, this does conclude the first portion of the presentation on C-axis and Y-axis. If you think you're interested in a sub-spindle lathe in the future, feel free to hang on. Those of you who do have a sub-spindle lathe, that's what the next portion of this presentation will cover. There's a few G-codes that we like to use associated with sub-spindle programming. Some of these are not only sub-spindle specific, but they do get used most of the time in part transferring. G22 is torque skip. What torque skip allows you to do is feed the sub-spindle, such as a chuck jaw that has a solid stop or a collet into the shoulder of the workpiece itself, feed onto the workpiece and tell the machine to press on the workpiece with, say, 15% W-axis load. This ensures that your workpiece is seated flat before clamping the chuck jaws onto the workpiece. Then you can pull back, cut off, and you're sure the workpiece is seated flush. G23 is a torque limit check. This can be used for a safe move. So feed safely onto, say, a clearance point or up to the face of the part before jumping into a torque skip move. And if the part is sticking out farther than the program allows for, the machine will only go up to, say, 20% W-axis load, and then alarm out saying you've put too much load on the ball screw on the servo motor. We can't feed any further. You don't want to. This will prevent damage in the machine, such as rapiding a subspindle into a part at 100%. It'll just bump the workpiece, throw an alarm. Okay, I need to back off a little bit or figure out why things aren't lining up. G28 cancels the torque limit command, and G29 tells the machine our maximum torque limit for our torque skip or torque limit check operations. Typically, G29 would be followed by PW equals some load, 30%, or whatever axis you want to check. If you want to check Z axis for load, G29 PZ equals 25. G122 and 123 are used for LT machines only to command the W axis from the A turret or the B turret when doing a part transfer. And then our G140 main spindle mode command and G141 subspindle mode commands. These are the M codes used for the main spindle when doing a part transfer. We have chuck, clamp, and unclamp, M83 and 84. Air blow on off. It's nice to blow air on the workpiece as you feed over. Make sure everything's nice and clean and you're not packing any chips onto a nice turn finish. M88 and 89 will blow air from the main spindle side. M151 and M150 are your spindle synchronization commands. We're going to use this to sync the two spindles together for a successful part transfer. M185 and M184 allow the main spindle to be unclamped and rotating for the part transfer. And then M976 allows the W axis to feed past the turret face, saying that I understand there's interference mathematically in the W and Z axis, but that's because you intend to come past, grab the part, and then pull back before cutoff. These are the M codes associated with the subspindle during a part transfer. M246 and M247 allow the subspindle to rotate while unclamped. Then we have our chuck, clamp, and unclamp for the subspindle, and our air blow on off for the subspindle. Now, an important note, the way these commands work, if I'm in the G140 coordinate, my subspindle is my M246, M248, M288 spindle, my subspindle. If I'm in the G141 coordinate plane, I'm saying I'm in subspindle mode. These M codes will command the main spindle, and the main spindle M codes will command the subspindle. So I like to do all of my part transfers in the main spindle mode. I talked a little bit about torque limiting function. This is the cutout from the programming manual on what torque limiting command does, and this is what it would look like. So G29, P, triangle. You can see triangle is your axis. So for a subspindle transfer, we would have G29, PW equals 30. Now this only works when the parameter in other function 2, max limit for torque limiting function, is set. Typically, I set that to 75% on a new machine. And then we can use G29 to limit further down to 25 or 30 or whatever we desire. But if that other function parameter is 0, G29 will alarm the machine every time, even when being used correctly. And then G28 cancels the torque limit command and allows the machine to torque at maximum output again. This is an example of a torque skip line command. G22 would be our torque skip G code. Z here is representing our target point. For a part transfer, let's replace Z with W. So if I want to feed W to -1/2 inch, I then have to give the machine a tolerance. So D is my distance that I'm allowed to come up short of my target point. So let's say I use 50 thousandths. I'm allowed to hit my torque commanded by my PW equals somewhere between 1/2 inch, my target point, and 450 thousandths, the shortest I can come up based on my D tolerance. L is the distance of which I can overrun my target point. So if I can be within 1/2 inch and 50 thousandths overrun, I'm looking between 1/2 inch and 550. That means my total allowable range to torque seat onto my part would be 450 thousandths to 550 thousandths with the torque skip command. And it will torque on at a feed rate defined by F to the preset torque value of PW equals on this line. This will not match your G29 command. This will need to be less than your G29 command. G23 has the exact same command format, except like I said, it's a torque limit check command. In this case, you do not want the axis of the machine to reach the torque limit defined. If it does, that's when the machine will alarm out saying you've had a crash or a bump into your workpiece and the machine has stopped before damage occurs. Now you must figure out what's not lining up and how to fix the issue without having a crash that causes damage to the machine tool. This is a sample part transfer program. N1899 is typically the sequence name I will use for my part transfer. We're canceling the tool offset and moving the turret to the limits, turning on the spindle at 1000 RPM, and then taking the turret to Z0. Now, in this case, Z0 is the face of my chuck. So I'm going past the workpiece to get the turret out of the way to allow the subspindle to come in. Or Z0 could be the face of your part if there's enough clearance to pass up your part off tool, and then you're ready for your cutoff operation. G18 says put the machine in the XZ coordinate plane for all arcs. And then M247, now we're saying the subspindle can rotate with the chuck unclamped, because I want the chuck to be unclamped when I come in to grab my part. Once the subspindle is allowed to rotate unclamped, then we can turn on spindle sync with M151. Then we turn on our air blow for both spindles to get ready to feed on and clean the part. M976, turn off my W-axis interference so that I can pass up the turret to grab my workpiece. Rapid to 1 inch away from the end of the part. Put the machine in feed per minute mode and limit the torque command to 20% load. Now we're using a torque skip move to feed 2.5 inches onto the workpiece. We're allowed to come up 50 thousandths short or overrun by 50 thousandths. If we torque out at greater than 50 thousandths short or overrun by more than 50 thousandths, the machine will alarm out. And we're trying to feed into the workpiece at 15% load to know it's seated at 40 inches per minute. Once we've reached our torque skip position, we shut off torque limiting command with G28, clamp the subspindle, turn off the chuck interlock release so that our subspindle does not think it can rotate unclamped anymore, because now we intend to hold the workpiece. If the chuck comes unclamped, we want to know and we want the machine to alarm from this point forward. Turn off air blow and allow the main spindle to rotate while unclamped. Then unclamp the main spindle. Rapid the W to the limit. In this case, we don't have a cutoff operation. We're just transferring a casting or a blank. If we had a cutoff operation, we might only rapid 3 inches ahead or our part length ahead to get ready to cut off our workpiece. We've transferred our workpiece to W50. Take the turret back over to my Z limit somewhere near the middle of the machine. Turn off spindle sync. Go into subspindle mode to get ready to do my subspindle machining work. And then one more time, take the turret to the Z limit of the subspindle. And an optional stop. Does anybody have any questions?
Yes, we do. Somebody was asking that they're familiar with using local variables, but they were not familiar with seeing the CRC in their program, and they were wondering if you could explain that real quick.
CRC is just a local variable I defined, as in cutter radius comp, and I'll back up to that slide. I'm using CRC to add or subtract based on which direction I'm moving the radius of my tool. So CRC is just a local variable that I created that made sense to me, standing for cutter radius comp. And then in the program, I'm doing math with the value I set it equal to.
I believe that was all the questions.
All right. If anybody has any other questions after we get off here you think of, we now have an AE support system. That phone number is below in the right corner, 314-684-4200. For St. Louis, that will ring all of the engineers that are in the office phones, and whoever's available will pick up and help you out. Or you can email aesupportstl@hartwiginc.com. Again, that emails all of the engineers in the office, and whoever's first available can respond to your question and work with you one-on-one and help you out. Or my contact information is on the left. You're also more than welcome to always reach out to me by phone or by email. Thank you guys for attending today, and enjoy the rest of your day.